Hello, I'm Paul Dichtel. I'm a researcher in the Quantic team at Imperial College London. We are investigating imaging with undetected photons, and I would like to talk to you about broadband nonlinear frequency mixing, which is concerned with the light sources for this project. So when you want to do imaging with undetected photons, you would use a nonlinear interferometer that you can see here and that Nathan was describing in the other talk. But of course, you need a process to generate the signal and idler photons that would then, be inserted into that setup. And when you're using a conventional nonlinear crystal, there are certain problems. For example, it's very sensitive to alignment. The overlap problems of the pump beam and the idler beam, which becomes very large when you try and push it towards the infrared where you want to do the imaging. And of course, the absorption of the crystal itself is a problem, because all those nonlinear crystals start absorbing in the infrared, and they would simply just absorb all the idler photons. So in order to overcome those limitations, we propose to use a metasurface, which is an artificially engineered material with nonlinear properties that we can design. And the key idea is that it's composed of nano-sized building blocks where the nonlinear interactions happen, so in really tiny volumes here. And we can avoid phase matching constraints in that way. And yeah, as I said, thanks to those plasmonic resonances, we would get very efficiently, very efficient nonlinear frequency mixing. And this can be extended in the future. For example, this can be coated with highly nonlinear polymers, and we've got lots of freedom in designing those structures, and that's what makes them very attractive. So far, we've managed to support second and third order nonlinear processes at the same time in those metal nanostructures, and we've shown frequency mixing in the visible and infrared part of the spectrum. And to demonstrate this, we've, for example, characterized two pulses at the same time, one being at the edge of the visible spectrum at around 800 nanometers, and the other one being at 1.5 microns, so in the near infrared. And more recently, we've developed a new design, which you can see in the bottom left, and we've managed to push this upper limit of wavelength even further into the infrared, so 2.5 microns at the moment. And of course, we want to eventually go even further than that so that we get access to more molecular transitions, which of course will be very valuable for chemical and material analysis, and of course for medical applications. So at the moment, we've got a system called DigiStain for cancer detection in tissue samples. So infrared photons would interact with the sample. But at the moment, it's still relying on thermal detection. And we want to replace this with detection in the visible photons. And that's what we need those light sources for. Thank you very much from all of us from Imperial College London.